Okay, good morning, everybody. So today we're going to be talking about stability. And in particular, we're going to be talking about bounded input, bounded output stability. And we're going to be introducing a tool that will help us determine the stability, which is the Routh-Hurwitz table. So if you look at a linear time invariant system, let's see what we mean by bounded input, bounded output stability. If we have an input that is applied to it, u of t, that has a Laplace that is u of s, and we have the system impulse response g of t, and we have our output y of t. Then, as we know, the output y of s is going to equal to g of s multiplied by u of s, and y of t is going to equal to g of t convolved with u of t, which is equal to the integration from 0 to t, g of tau, u of t minus tau, d tau. Again, convolution in the time domain is multiplication in the frequency domain. Now we're going to see what happens if we applied an input, u of t, that is bounded in the time domain. So u of t might look something like this. The maximum of it is n, and this n is smaller than another limit, which is m. So the input is bounded. So u of t is bounded such that the maximum of u of t is less than or equal to n, and this n is less than m, and it is finite, is less than infinity. And what we're going to do is we're going to calculate the output y of t. So if we calculate the output and take the absolute value of that output, is going to equal the integration from 0 to t, g of tau, u of t minus tau, d tau. However, this u of t minus tau is finite. It has a maximum value that is finite. And therefore, if I take the absolute value of the integration, this is going to be less than or equal to the integration from 0 to t, the absolute value of g of tau, u of t minus tau, d tau. What does this mean? If I take the integration of g of t or g of tau multiplied of t minus tau, I might have g of t multiplied by u of t minus tau looking something like this. But if I bring the absolute value inside, then I'm going to get something that looks like this. Is that clear? So this integration, if I take the absolute value, I'm going to be subtracting this from this. So this is going to be always smaller or equal to this. If it's all positive, it's going to be equal. But if I have positive and negative, then the negative is going to subtract from the positive, and is going to be less than. So it is always going to be less than or equal to the integration of the absolute value of g of tau multiplied by u of t minus tau. Okay. So continuing, the integration from 0 to t, absolute value of g of tau, u of t minus tau, d tau, is going to equal to the integration from 0 to t. I can take the absolute value of g of tau multiplied by the absolute value of u of t minus tau, d tau. But this u of t minus tau has a maximum value of m. So therefore, this integration is going to be less than m multiplied by the integration from 0 to t, the integration of g of tau d tau. Together? Is that clear? So therefore, if I want the output to be bounded, what do I have to have? I need to have this integration to be bounded, because this is equal the value of y of t. So therefore, the sufficient condition for y of t to be bounded is that the integration from 0 to t of the absolute value of g of tau d tau must be bounded. Together? Y of t is going to be less than m multiplied by this integration. If I want that to be bounded, then if this is bounded, y of t is going to be bounded. Okay, so let's look at an example. If I have g of s that is equal to 1 over s plus 1 multiplied by 1 over s minus 2, I can do partial fraction expansion and write this as 1 over 3 multiplied by s minus 2 minus 1 over 3 divided by s plus 1. And therefore, g of t is going to equal 1/3 e to 2t minus 1/3 e to negative t, which is equal to 1/3 e to 2t minus e to negative t. What is this g of t? What do we call this g of t? What is it? G of s is the transfer function. If I take the inverse Laplace of it, what is it? Knowing that you guys are tired, I'll take that answer. This is the impulse response. Okay. So g of t of this system, g of s that has a transfer function 1 over s plus 1 multiplied by 1 over s minus 2 is given by 1 over 3 e to 2t minus e to negative t. So if I want to determine whether this system is stable or not, what do I have to do? I'm going to have to apply this rule, integrate from 0 to infinity, 0 to t to infinity, g of t dt, and see if I get a finite value or not. And if I integrate this, it's going to equal 1 over 3, the integration from 0 to infinity, e to 2t minus e to negative t dt, which is going to equal to 1/3 multiplied by 1/2, 2 to 2t plus e to negative t from 0 to infinity. Together? Is that clear, everybody? Okay, so if I look at this, is this bounded or not bounded? If I take the integration, 1 half multiplied by e to 2t from 0 to infinity. What is this going to give me? It's going to give me infinity, isn't it? 2 to infinity is going to give me infinity. So is this system stable or not stable? Not stable. Therefore, this system is not bounded input, bounded output stable. Okay. And we can see why it is not stable. If I have an input that is equal to u of t, what is the output going to equal to? It's going to equal 1/3 the integration from 0 to t, 2 to the power of 2t minus e to negative t dt. And this is going to go to infinity as t goes to infinity. Is that clear? Where is this coming from? If the input is u of t, then the output is going to equal the integration from 0 to t, 2 to 2t minus e to negative t dt. Anybody knows? Seen something similar in the lab. Okay, so g of t looks something like this. It's going all the way to infinity. And I want to convolve it with u of t. U of t is a unit step. How do we convolve them? We flip u of t, and that will be the output when t is equal to 0. Then I will slide it. And that will be the output at whatever slide I have. So what is that going to look like? If I flip this, it's going to look something like this. Together? And then I start sliding it. It's going to look something, and this is t, the output at t. And multiplied by this is going to be the integration from 0 to t, and this is just a 1, because it's a unit step, multiplied by g of t. Does that make sense, everybody? Just so happens when the input is u of t, the convolution is easy. It's going to just equal the integration from 0 to t of g of t. Just because, again, u of t, when we flip it, is going to look something like this, and then when we slide it by t seconds, we multiply these together, it's going to equal the integration from 0 to t. This signal is 1 multiplied by g of t. So I feel like this is 1 multiplied by this. Does that make sense, everybody? Okay. So therefore, if you look at the stability, let's look at the stability and the location of the poles of the system. And let's assume we have a system with simple roots. So we have g of s that is equal to k1 over s minus p1 plus k2 over s minus p2 all the way to kn over s minus pn, which is equal to the summation of ki over s minus pi. So So this is our transfer function. Now if I calculate the impulse response, which is the inverse of the transfer function, I'm going to get g of t. What is g of t going to equal to? K1 P1 multiplied by t plus K2 e to P2 multiplied by t all the way to Kn or K sub n e to P sub n multiplied by t, which is equal to the summation of Ki e to Pi multiplied by t. Now if I take this and integrate it, if I integrate the absolute value of g of t, when is this integration going to be bounded? When the result is finite, and what is the condition on P1 to Pn for that to be the case? They have to be negative. Does that make sense? If I integrate e to negative 5 multiplied by t, it's going to be finite. If I integrate e to 5 multiplied by t, it's going to go to infinity. Together? But what is that part of the, in general, p, all these poles are complex. So what part is important for it to be negative? The real part. All the real part of the poles, i's, has to be less than 0. Is that clear? Makes sense? Just like we've seen in the example that we've just done. If I look at this example, this real part is positive, therefore it goes to infinity. This is going to decay, it's going to go to a 0. So all the real parts of the poles have to be less than 0, and that is the same as saying the poles are in the left half plane of the S-plane, in the left half of the S-plane. Is that clear, everybody? Okay. Okay, so let's see what happens if we have poles that are on the j omega axis. So in this case, if the poles are on the j omega axis, the output is a sustained oscillation. Unless the input is a sinusoidal signal that has the same frequency as the j omega poles locations. Frequency equal to the locations of the poles on the j omega axis. What happens in this case? It starts growing, yes. In this case, the response becomes unbounded. And what do we call the system? Marginally stable. Okay, so let's look at an example and see how that works. So let's say we have a system that has a transfer function g of s that is 1 over s squared plus 1. Where are the poles of this system? Anybody want to guess? Yes. Plus or minus j. Who said I?
J.
I mean, in physics, they use I. We use j. Okay. So the poles are on the j omega axis. So therefore, omega is equal to a 1. So therefore, if I apply r of t, or actually let's apply first a finite, a signal that does not have poles at 1. So if I come to this system, 1 over s squared plus 1, and we apply to it a unit step. So this is 1 over s. What is the output C of S going to equal to? What is C of S equal to? Anybody?
1 over s times s squared plus 1.
Thank you. Now many people in the exam forget to multiply by 1 over s. That's why I emphasize it. Okay, so what do we do next? We can do partial fraction expansion. We can expand this as 1 over s minus s over s squared plus 1. And therefore, the output is going to equal to u of t minus cosine of t. And therefore, how does this output look like? It's going to look something like this. This is C of t. Is this bounded or not bounded? Bounded. Yeah. I mean, it has a maximum value. This is the maximum value. It does not exceed it. So if it was only for input like this, we'll call this stable. However, let's see what happens if we apply to this system a sinusoidal signal that has a frequency that is equal to the location of the poles of this system. So what is this frequency going to equal to? What is it? 1? Yeah? 1. So if we have r of t, that is equal to cosine of t. And what is the omega if this cosine of t? 1. Omega equal to a 1. And since omega equal to a 1, it is equal the location of these poles. So let's see what happens at the output. So we're going to take the Laplace of the cosine, which is going to be s over s squared plus 1. And then we're going to multiply it to the system, which is 1 over s squared plus 1. So therefore, C of s is going to equal s over s squared plus 1 multiplied by 1 over s squared plus 1, which is going to equal to s over s squared plus 1 over all squared. And if I look at the lookup table, I can take the inverse Laplace of s over s squared plus 1, and that is going to equal to 1/2 multiplied by t multiplied by sine of t. And therefore, what does the output look like? Excellent. It's going to continue to grow. It's going to look an oscillatory response that is going to continue to grow. Is that clear? Makes sense? So therefore, in this case, we call the system marginally stable. So this is bounded. This is unbounded. And keep in mind, the input signal that will cause the system to become unbounded has a frequency that is equal to the location of the poles of the system. Is that clear, everybody? Okay. Now I know we've done lots of stability discussion in the lab. So hopefully after this class, when you go back and look at the lab reports, they will make much more sense than they did before. Okay. So let's look at a system and see whether it is easier to determine the stability by finding all the poles or finding a range of values that makes the system stable. So let's say we have a system that is given by the following block diagrams. S squared plus 4 multiplied by s plus 2. This is our plant. This is our controller. And we have our input R of s, C of s. So we're going to calculate the closed loop transfer function, T of s. We're going to equal to 2 multiplied by k divided by s multiplied by s squared plus 4s plus 2 divided by 1 plus 2k divided by s multiplied by s squared plus 4s plus 2, which is going to equal to 2k divided by s cubed plus 4s squared plus 2s plus 2k. Now when we look at the system like this plant itself might be unstable, but what we are interested in is the closed loop system to be stable. So how do we determine if the closed loop system is stable?
Check the input or
No, the stability is not related to the input. I mean, keep that in, I mean, that's a key point. The stability is a characteristic of the system. It has nothing to do with the input. The input is always assumed to be bounded. Does that make sense? So therefore, the stability is a characteristic of the system. Okay. So what we like to do, if we are designing a controller, I mean, this is a controller. For some reason, we chose the controller to be like this. And therefore, we want to know what are all the values of k that will make the system stable. So we like to be able to determine stability for a range of values of k. So then we're going to ask a question: is finding the number of roots in the right half plane easier than solving the equation for all the roots? What does this mean? So if you want to determine the stability of this system, we have two options. What are the two options?
Finding all the roots.
Finding all the roots, and then see where these roots are. What is the second option?
Just the roots that make it unstable.
Okay, that's the second option. What is the third option? Just finding the number of roots that are in the right half plane without knowing where they are. Does that make sense? So we can solve for all the roots and say, okay, these are the roots. Okay, yeah, we have two roots on the right half plane, therefore the system is unstable. Or we can just look at this and say, oh, it has two roots on the right half plane. We do not know where they are, but it has two roots on the right half plane, therefore the system is unstable. Make sense? And this is the approach we're going to be doing. So what we're saying is, if we are given this characteristic equation, which is 4s squared plus 2s plus 2k, we have two choices. We can find all the roots, of course, if we have MATLAB, that should be easy, but if you're doing it without the computer, that is going to be tedious. The second option is just to determine the number of roots in the right half plane. And this is going to be easier. Is that clear? So what we're going to be doing next is not finding where the roots are, but rather determining how many roots does a characteristic equation have in the right half plane. And we're going to show that there is a tool that will help us solve for the number of roots that are in the right half plane. Together? Okay. So the next thing we're going to look at is the relationship between the roots and the coefficients of a polynomial. What is going to determine the location of the roots? The coefficients of the polynomial, isn't it? One polynomial, how is it different than the other? From the coefficients of that polynomial. So let's see what is the relationship between the pole's location and the coefficients of the polynomial. So let's take a second order system polynomial. And let's say this polynomial has two poles that are P1 and P2, which we can write as s squared minus P1 plus P2 multiplied by s plus P1 multiplied by P2. And this polynomial is s squared plus a1 multiplied by s plus a0. So if we have a second order polynomial, how are the coefficients of the polynomial related to the location of the poles? These P1 and P2 are the location of the poles. How are they related to the coefficients of the polynomial? By this equation, A0 is equal the multiplication of the poles. A1 is equal negative the summation of the poles. You see it? Everybody? Okay. So therefore, A1 equal to negative P1 plus P2, which is equal to the negative of the sum of roots. And A0 is equal to P1 multiplied by P2, which is equal to the product of the roots. Okay, let's do another example. If we have P3 equal to s cubed plus a2 s squared plus a1s plus a0, and we have three poles, P1 or three roots, s minus P2, s minus P3. Now if you multiply these three terms, we're going to be getting s cubed minus P1 plus P2 plus P3 multiplied by s squared plus P1 P2 plus P2 P3 plus P1 P3 multiplied by s minus P1 P2 and P3. So what are the coefficients? How are the coefficients related to the location of the poles? A2 is the sum. A1 is the multiplication with I not equal to j, all the terms. P1, P2, 2, 3, 1, 3. And A0 is the multiplication of all the roots. So we can generalize this. If I have an nth order polynomial, Pn of s equal s to the n plus an minus 1, s to the n minus 1, all the way to a0, and we have n poles or n roots, s minus p2, all the way to s minus pn, then these coefficients are related as follows. An minus 1 is going to equal the negative of the summation of pi's. An minus 2 is going to equal to the summation of pi multiplied by bj, where I is not equal to j. And a0 is going to equal negative 1 to the power of n, p1, p2, all the way to pn. Together? We can see this here. And in general, we can generalize it to any order using these rules. Okay, so let me ask you a question. So what is it we're trying to do? We're trying to determine how many roots are in the right half plane. Together? So we're trying to determine how many roots have a negative real part. And therefore, if I look at this expression that I have here or the expression that I have here, if I have all the poles that are in the left half plane, what are all these coefficients going to look like? What's going to be common about all these coefficients that I have here? A2, A1, and A0.
They all be negative.
The opposite.
Positive.
They are going to be positive. If all these roots are in the left half plane, then all these coefficients, P1 is going to be negative, 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 multiplied by negative is going to be positive. Negative by negative, positive. Negative by negative, positive. Negative by negative, positive. These three are going to be negative, multiplied by negative is going to be positive. And the same thing applies for any order. Does that make sense? Remember, we have it as S minus P1. So if it is in the left half plane, P1 is negative. Together? So it's going to be S plus 5. The 5 is going to be in the left half plane. Okay. So therefore, based on this, we can see that if all the roots have negative real part, then all the coefficients are going to be greater than 0. If all the roots have negative real part, which means they are in the left half plane, then all the coefficients of the polynomial are going to have a positive coefficients. Okay. So based on this, we can conclude also if there is at least one coefficient that is less than or equal to 0, then that will mean that there are roots on the j omega axis or in the right half plane. So if there is at least one coefficient, one AI, that is less than or equal to 0, that will mean there is or there are roots on j omega axis or in the right half plane. Does that make sense, everybody? So if I look back at the generalization here, if this term is 0, the only way this term is going to be 0 if one of these is a 0, isn't it? The same thing, the same thing applies to all the coefficients. And if any of these coefficients is negative, the only way it's going to be negative if one of the PIs is going to be positive. Together? So therefore, we can conclude if all the roots have a negative real part, then all the AIs are going to be positive. And therefore, if I see a polynomial that have at least one coefficient that is 0 or less than 0, this must have come from a pole or from a root that is either in the right half plane or on the j omega axis. Okay, so let's look at a few examples to illustrate this. So let's say we have a polynomial s plus 1 multiplied by s plus 2. This is going to be equal to s squared plus 3 multiplied by s plus 2. What are the roots that I have here? Negative 1 and at negative 2. They're on the left half plane. And if I look at the coefficients, what are the coefficients? Positive, positive. Make sense? Okay, another example. We have two poles, -1 plus j, and P2 equal -1 minus j. So this is going to be s plus 1 minus j multiplied by s plus 1 plus j, which is going to equal to s squared plus 2s plus 2. Where are these poles? In the left half plane, yes. And if I look, so these poles are left half plane. And if I look at the coefficients here, what are they? Positive and positive. Okay. Let's look at a third example. If I have a pole at -1 plus j, a second pole -1 minus j, and a third pole that is at 1. What are the polynomial is going to equal to s minus 1 multiplied by s plus 1 minus j multiplied by s plus 1 plus j, and it is going to equal to s cubed plus s squared minus 2. How is this consistent with what we're saying? It has a negative for coefficient, and what else?
The 1 is positive for the pole.
Yes, and it has a missing s, isn't it? So this is going to equal to s cubed plus s squared plus 0 multiplied by s minus 2. We have a term missing, and we have a negative coefficient. Okay. So let's take another example. I'm going to determine the stability of the system below. Okay, so to determine the stability, we're going to calculate the closed loop transfer function and calculate the characteristic equation, which is going to be the denominator of the transfer function. And that is going to equal to s to the 4 plus 4 s cubed plus 5 s squared plus 2k. What are the values of k that will make this system stable? Positive ones. Yeah. What are the values of k that will make this stable? What? It's missing a term. So is there any value of k that will make this stable? No, because it's missing a term. So this is missing a term s to the 1. So therefore, we're going to always, the system always has roots in the right half plane. And therefore, it is unstable for any value of k. Is that clear?
If you input like an integrator, would that make it stable?
No.
Like 1 over s?
Well, 1 over s is a unit step. This will be unstable for any input. Does that make sense? For any input that is bounded. any bounded input, this system is unstable. Again, the stability has nothing to do with the input, it has to do with the system. This system has a root that is in the right half plane. So therefore, it's going to have always a term that is going to be exponentially growing. So even though I might apply a finite input to it, it's going to have an output that's going to go to infinity. Make sense? Okay. Okay. So therefore, it looks like we're done. We can just look at the polynomial and see if it has any missing terms or if it has any term that is negative, isn't it? And then we can determine stability. Why do we need to spend another lecture on this topic? And therefore, if we answer this question with yes, we can move on to the next topic. So is this a reliable way to assess or to determine stability? And what is the answer going to be? It's your call.
No.
It's going to be yes and no. If it was not for this no, we would have moved on. Okay, let's see why. So let's take another example. We have a characteristic equation that is SC cubed plus 4S squared plus 5S plus 20 equal to a 0. What does this look like? Looks like it has all the terms, it has nothing missing. All the terms are positive, aren't they? And therefore, you would think this will be stable. You'll think all these poles are going to be in the left half plane. However, if you look at the poles for this polynomial, P1 is equal to -4, great. P2 is equal to J2.33, and P3 is equal to -J2.33. So what do we conclude from this?
It's 2 poles on the J omega axis.
We have 2 poles on the J omega axis, even though all the coefficients are positive and nothing is missing. Make sense? So anybody confused?
So it's at least marginally.
So would that be marginally stable?
Well, this is marginally stable, but for our purpose, it is unstable. Yes, it's marginally stable. So for our purpose, it's not stable. Does that make sense? So what do we conclude from this technique and from the coefficients?
It's not
You can't always
reliable.
trust it.
That's one way of expressing it. So what we got is we got a necessary condition for stability, but not a sufficient condition for stability. Does that make sense? So if any coefficient is missing or negative, we can conclude it's unstable. If all the coefficients are there and positive and none is missing, we do not know. It could be stable, it could be unstable. Okay. So therefore, we got only a necessary condition for stability. But not a sufficient condition, but not sufficient condition. And therefore, if at least one coefficient is missing, or if it's negative, then the system is not bounded input, bounded output stable. If all coefficients are positive, we cannot tell. Okay. So therefore, we need a tool that will help us determine how many roots are in the right half plane. Again, if we are giving a polynomial, if it is missing or if it has any negative coefficients, then we can conclude the system is not bounded output, bounded input, bounded output stable. But if all the coefficients are positive, then we have to find another tool that will help us determine the stability. And that tool that we're going to be introducing is called Routh-Hurwitz stability criteria. Okay. So what is this tool? This is an analytical procedure that will help us determine if any of the roots of the system has a negative real part. And this tool will give us the number of roots that have a positive real part. Together? Okay. So let's see how this tool works. Now this tool is straightforward. However, there are special conditions or special cases, and we will highlight them. So just keep that in mind when you're using the tool. So let's say we have a polynomial, P of S, an s to the n, an minus 1, s to the n minus 1, a1 to the s, plus a0. Where does this polynomial come from? If we are studying a system.
Like the definition function or the
Which one?
C over S function that we have for
Uh,
denominator.
the denominator of the closed loop transfer function. Together, keep that in mind. So if we have a system that we're trying to determine the stability for, we're going to calculate the closed loop transfer function, and then we're going to take the denominator. Is that clear? Keep that in mind. This is the polynomial we're referring to. Similar to what we've done in these examples. So here is the system. When we determine the stability, we calculated the closed loop transfer function. This is the denominator of the closed loop transfer function. Okay, so let's see how this tool works. So the first step, we're going to form the Routh-Hurwitz array. And what we're going to do,
Sorry.
wake up. S to the n. That might explain. s to the n minus 2, s to the n minus 3, s to the 0. Okay. So then we're going to put the coefficients an minus 2, an minus 4, etc. And then we're going to put an minus 1, an minus 3, an minus 5, etc. And then we're going to calculate B1, B2, B3, B4, and then we're going to calculate C1, C2, C3, C4. And the way we're going to calculate these. Okay. So the first two rows of the Rao-Hurwitz table are going to come directly from the polynomial. All the rest of the rows are going to come from calculating these coefficients. And these coefficients are given by the following. B1 is going to equal to negative 1 divided by an minus 1, the determinant of an minus 1, an minus 2, and an minus 3. B2 is going to equal negative 1 over an minus 1, the determinant of an minus 1, and then an minus 4, and an minus 5. And so on. B3 is going to be an minus 6 over an minus 7. And C1 is going to equal to negative 1 over B1, the determinant of an minus 1, B1, an minus 3, and then B2. And C2 is going to equal negative 1 over B1, the determinant of an minus 1, B1, an minus 5, and B3. Can anybody see the pattern of how we calculate it? Okay, so when we calculate, these two rows are already come directly from the polynomial. When we calculate this row, it's negative 1 over this element, and then we're going to take these two, calculate the determinant. Then we're going to take these two, calculate the determinant, these two, and calculate the determinant. Make sense? So B1 is going to equal negative 1 over an minus 1, and the determinant that is established by these two. B2, negative 1 over an minus 1, the determinant established by these two, and so on. And then we're going to calculate this row. When we calculate the row after it, C1 is going to be the same thing. Negative 1 divided by B1. And then we're going to calculate the determinant using these two elements and these two elements. C2, negative 1 divided by B1, these two elements. Make sense? Everybody sees it? You don't have to memorize it, so you can just... Okay. So let's do an example and calculate that. So for each element, for each coefficient, we take determinant formed by the first coefficient and I plus 1 columns of two preceding rows, and we divide by first element of preceding row. Okay. Okay, so let's do an example on the calculation. So we have a polynomial P of S that is equal to S cubed plus S squared plus 2 S plus 8. So apparently this coefficient is 1, this coefficient is 1. So we're going to come here. We're going to make the columns. That's going to be S cubed, S squared, S to the 1, S to the 0. And in the first row, we're going to have a 1 and a 2. Where is this one coming from? This one is from here, yes, and the 2 is from here. So 1, we skip 1, a 2. The second row is going to have a 1 and an 8. So this is this one, and this is this 8. Together? So then we draw our line. And we start calculating the new elements. So we have this element that we're going to calculate. And this element is going to equal negative 1 divided by 1, the determinant of 1, 2, 1, and 8. Which is negative 1 divided by this element. So this element here is this element here. Negative 1 divided by this, and then the determinant by these two. What is this determinant going to equal to? 1 times 8 minus 2 times 1. 6, and then we have a negative 1, so it's going to equal to a negative 6. Again, this is going to equal negative 1 multiplied 1 times 8 minus 2 times 1. Okay, there are no more columns to calculate more elements, so we're done with this row. We can come to the next row. Who can tell me what this row is going to equal to? You can add a 0 here. It's going to equal negative 1 over negative 6, and the determinant established by 1, negative 6, 8, and 0. Together? What is that going to equal to? What is it? It's going to equal to an 8, which is 1 over 6, 1 times 0 minus 6 times 8. Together? And you're going to see every time there is this pattern at 0 here, this element is going to come here. So you don't even have to calculate it. Okay, I'm going to stop here and we'll talk about the exam. Any questions on this? Questions? I mean, I know it's still maybe not 100% clear, but we're going to be doing lots of these calculations, so hopefully it will become very clear.